Hi everyone. In today's lecture, we will discuss about nonlinearity in cascaded systems. Okay. So in the previous lecture, just to quickly refresh, I discussed several kinds of nonlinearities that will exist in RF systems. The first metric to characterize nonlinearity is total harmonic distortion. And I also told you that total harmonic distortion is more of a specification for the transmitter. So meaning total harmonic distortion tells you if I feed a signal to a nonlinear system, it's going to produce a nonlinear system f of x. It's going to produce harmonics of, if I feed a signal of frequency f1, it's going to generate f1, 2f1, 3f1 and so on. Now we said in a low frequency system, like for example in an audio system, this might create hearing issues. A low pitch signal can be heard as a high pitch signal. Okay. But that's not the case with RF systems. We said most RF systems are narrowband systems, meaning most of the energy is concentrated in a very small range of frequencies. Now, if I apply this to a nonlinear system, what it's going to do is that it's going to create a term somewhere at, energy at, it will be of course lower, energy will be lower at say 2f1 and probably at 3f1 and so on. Now, if you look at this, this is not creating any direct problem to the signal itself, which is concentrated mostly at f1, but it might create problems for other receivers, which might be operating in this frequency, which is 2f1 or 3f1. We also discussed one example of a GSM. I told GSM has two operating bands. One is 900 megahertz and one is 1800 megahertz. So the second harmonic of the GSM 900 megahertz can create as an interferer. Can behave like an interferer for a 1800 megahertz system. Okay, so when you actually design a transmitter, you have to keep in mind that you have to minimize the harmonics. And what is the effect of nonlinearity on a transmitter? You have to reduce harmonic distortion. Okay, that is one effect we spoke about. Then we also discussed an important parameter called nonlinearity, which is the gain saturates as you keep increasing the input signal. Okay. And we said this is a compressive nonlinearity, and we took the example of one of the most commonly encountered compressive nonlinearity, which is third order nonlinearity, odd harmonic non-ideality. So which is characterized by this equation k1x minus k3x cube. Okay. So and we said why did we choose this? If you remember one of the lectures, we discussed that if you took a differential pair, I don't know. I can have any kind of device. I will just take an example of MOS device here with a constant current source, and then I tried to measure the current I1 and I2 are the currents on both the arms, and I've applied a differential voltage between these two terminals of value delta V. You can easily show that if you measure the difference between I1 and I2, it will be a function of delta V. Okay, so in fact you can show that it will actually be, I'll assume that the current flowing in this device will be some k times f delta V by 2, and this will be k times f of minus delta V by 2. So the actual function, the difference between I1 and I2 will actually be k into f of delta V by 2 minus f of minus delta V by 2. So if you look at this function is an odd function, which means it will only have odd harmonics of the input frequency. And usually what happens is that the harmonic strength keeps reducing as you keep looking at higher and higher harmonics, so which means the harmonic strength of f1 will be much greater than 3f1, and 3f1 will be greater than 5f1 and so on. So normally we approximate it to first harmonic, which is the first nonlinearity, which is the third harmonic. Okay, and that I took an example of k1x minus k3x cube, and we showed that for this nonlinear system, if I feed a sinusoid of signal A cos omega naught t as an input to this system, we showed that the gain actually starts reducing as you keep increasing the amplitude. Okay, and we said that the gain, what happens to the gain is actually when you substitute it and then expand this expression using cos cube theta, you will actually get the gain as k1a minus 3 by 4 k3 a cube into cos omega naught t. I am talking about the first harmonic term alone. See, here we are not talking about distortion. Distortion is what happens at a different harmonic. Okay, what is the energy level you are generating at a different harmonic. Now here the problem is gain compression. The gain is reducing as you keep increasing the amplitude. And we introduced a term called 1 dB compression point. We said to tell us how nonlinear the system is, we will characterize the amplifier. If I want to compare multiple nonlinear amplifiers, this is one good metric. It tells you how nonlinear the system is. We said the point where the gain reduces by 1 dB from its nominal value. And I told you that corresponds to approximately a 10 or 11% reduction, 11% to be exact, to be precise, reduction in the actual gain. So K1A minus 3 by 4 K3A cube will actually be 0.89 K1A. This is the ideally it should be 1 K1A, K1 into A, but as I said 1 dB compression point is where the gain reduces to 0.89. It is approximately 10% of its reduced by 10% of its nominal value. Now solving this, we found a 1 dB compression point, which is the point where the gain reduces by 1 dB, as 4 by 3 into 0.11. Okay, you can very easily show that this is the number. So into K1 by K3. So this is what we found, and this actually turns out to be 0.145 into K1 by K3. So this is the 1 dB compression point, and this is the peak amplitude. So the units will be for this will be volt. If I want to express, you can also express it as peak to peak by just multiplying it by 2. We can also express it in terms of in power by expressing it in dBm. Assume here I have to give you what is the kind of resistance. I mean, if I tell you it's a 50 ohm system, then you can simply find a 1 dB square by 2R will give you the power. Normalize it to 1 milliwatt and take 10 log of 10 dB, you will get the power in dBm. So we said power can be expressed in dBm or in amplitude for a nonlinear. The compression point, a 1 dB compression point, can be expressed in either power in dBm or in amplitude in volts. Typical numbers for this, I didn't discuss much about it. We even talk about receivers. Receivers also we can talk about P1 dB both for receivers and transmitters. Okay, for the receivers it is normally described at the input, because the signal that you are going to receive is always at the input. For transmitters we also mention it at the output. Okay, you know the gain at the amplitude at the compression point. This is a 1 dB is the input amplitude. So mind you, that's the input amplitude. So if you want to find the output amplitude, you just have to multiply it by the gain at that point. So which will be 0.89 into K1 into a 1 dB will give you the output. I will write it as a naught 1 dB. This will be the output amplitude. So similarly you can compute the power at the output. For receivers, typically this number is around 20 to 25 dBm, minus 20 to minus 25 dBm. So which turns out to be in the order of few millivolts peak to peak. Okay, some 60 millivolts peak to peak or so. Okay, I mean I'll just use this conversion. So for example 0 dBm corresponds to 632 millivolt peak to peak. So this is the result, you can remember this. So minus 20 dBm, so which means power is reduced by 10 power minus 2. So it will be 10 power minus 2 of 1 milliwatt. So that if you see the difference is 10 power minus 2. If power reduces by 10 power minus 2, then the voltage will reduce by root of that. So 10 power minus 1. So you will get 63.2 millivolt peak to peak. So that's how you can find that. Okay. So this is the typical numbers that you will encounter in receivers. So this was the discussion we had about compression point. And we also said why do we care about nonlinearity is that especially when you create an interferer, you can create a signal. Now I'll talk about the receiver. I've spoke receiver. At the receiver you normally have a low noise amplifier which can be pretty nonlinear. Okay. So when you are receiving a signal, when you are receiving your signal in the presence of a large interferer and unwanted signal, we discussed that the gain can be compressed because of the unwanted signal. And we said that if the amplitude of the unwanted signal is high enough, it can completely desensitize the receiver. I mean, it will behave as though receiver will behave as though it has no gain for the input signal. This is the signal you are supposed to amplify, but your receiver will not be able to do that because of the presence of this interferer. Which is why normally we'll see probably in the later lectures, we'll have to introduce filters around the channel of interest, the bandwidth of interest, so that you keep this signal within certain limits. We also use the word called blocker and interferer. I use the word called blocker and interferer to characterize that this interferes with the reception of the main signal. Now, why do we talk about cascaded systems? I'll now come about why do we talk about cascaded systems, and then we'll start discussing about the problems with cascaded systems. Normally what happens is that when you have a tower has a large range of coverage. You can be anywhere. It will normally have few kilometers, few hundreds of meters. So 0.5 kilometers to 1 kilometer will be the radius of coverage for a tower. Now, a tower is supposed to cover you even if you are very close to sitting very close to the tower, or you may be 100 times away from the tower. It should give you the same coverage. It should give you good, reliable communications. But you should understand, when you are staying very close to the tower, normally this is, again, I'll probably explain you later. If you assume that the tower is an isotropic source emitting power equally in all directions, okay, so I can assume PD is the density of power per unit area, multiplied by 4 pi r square, where r is the distance between the tower and the receiver. So this is the surface area of a sphere, multiplied by the power density, you will get the total power transmitted. Remember, the total power is constant. That's the total power that you are transmitting. Now, if you are very close to the antenna, you are very close to the tower, you can see that the density of power, so this is I will compute the density, power density will be total power transmitted divided by 4 pi r square. That I will multiply it by the area of your antenna, of the receiver antenna, which is your cell phone antenna. We also use something called aperture. I will call it A into A by 4 pi r square. This is the fraction of energy that power you will be receiving from your tower. See here, this doesn't happen in the current day scenarios. I am just assuming for hand calculation's sake. I am assuming power is equally transmitted in all directions. In today's antennas, we don't do that. We only transmit it in a very narrow beam. In fact, in 5G, we transmit the power from a tower in a very narrow beam, okay, in a very, very narrow range. If first we will find where the receiver is, and then you will concentrate, your beam will concentrate only on the receiver, the direction of the receiver. Okay, but today I am just assuming, for calculation's sake, I am assuming that the power is transmitted equally in all directions. So then this relationship will hold. So you have a sphere, surface area of a sphere is 4 pi r square. Now let's say cell phone occupies a very small area, A lambda, then the power that you will be receiving will be PT into A by 4 pi. A lambda, I have just called it A here. A lambda is the aperture area, or you can see it approximately as the area of reception of your antenna, receiving cell phone antenna. So this will be the power you will be receiving. Now I can stay 1 meter close to the antenna, or I can literally go 1000 meters away from it, 1 kilometer away from it. So when I am moving from this distance, the power is reducing by, see, if you see, it's reducing by 10 power 6 times. So for example, say that I am receiving at 1 meter 0 dBm power. At the distance of 1 kilometer, I will be receiving a power of minus 60 dBm. In fact, it will be even less. It can be even less. There is a phenomenon called multipath fading in RF systems, in wireless systems. I have not taken that into account. It can be even less, is what I am trying to say. So which means at the receiver, for example, let's say you are going to receive 0 dBm. Okay. Eventually, the receiver will be like this. So first you will have an antenna, and then you will have an amplifier which will amplify the signal. Then once you amplify it, normally I am drawing a conventional system. You will have a mixer which will down convert the signal. Sometimes you have something called as intermediate frequency. You will convert it instead of directly to DC. So you have your up converted signal. This is at some say center frequency F0. Your message is normally at the low frequencies. You can directly multiply it by F0. You will get the free energy at DC itself. That's called direct conversion receivers. But instead of doing that, we will actually translate it to an intermediate frequency. We will discuss later. It becomes easier to filter it. So it's called IF filtering. So we will have an intermediate filter called IF filter. After filtering it, then we will translate it to DC. So maybe this may be F0, FIF, F0 plus FIF. Then this will be FIF. It will translate to DC. Again, we will have some filtering there. Finally, it will be fed to an ADC, analog to digital converter, which will convert it to digital bits. So this will be your normal receiver structure. So if you see, your signal goes through a chain of circuits here. It goes through an amplifier, mixer, two band pass filters, or this is a band pass filter and this is a low pass filter, and finally to the ADC. Now say for example you are operating in a 1 volt system. Okay. Now what I want to do is, any signal that I'm going to receive, I'm going to fully utilize the ADC. I mean, the ADC has 0 to 1 volt is the entire range of the ADC. I want to expand whatever signal I'm receiving at the input to 0 to 1 volt. Say for example, I'm receiving a 1 millivolt signal. I want to expand it to 1 volt. Then all I need to do is I have to just multiply it by 1000 times. I need to have a gain of 1000. Okay. Now here I've assumed 0. I'll just come back to the problem of power reception. We have first received a power of 0 dBm, which translates to 0.6 millivolt peak to peak. Okay, I'll just take it as point or close to 1 millivolt peak to peak. Okay, this is just for analysis. Okay, so this is 0.6 millivolt peak to peak. Okay, I'm sorry, this is 0.6 volt peak to peak, or 632 millivolt peak to peak. For 0 dBm it corresponds to, or let me write it as 0.6 volt peak to peak, or 1 volt peak to peak. Approximately I'll assume 1 volt peak to peak. Okay, this is a very big, very weird approximation, but then I'm just using it for explaining an idea here. So at 0 dBm, assume that at or whatever power level here, I'm receiving a power of 1 volt peak to peak, signal of 1 volt peak to peak. What will happen at minus 60 dBm? The power is lower by 60 dB, so signal will also be lower by 60 dB. So I can say you will receive 1 millivolt peak to peak. Okay, if you remember, I said you should take root of, if 10 power minus 6 is in power, so 10 power minus 3 will be the voltage gain. So you will get 1 millivolt peak to peak. So which means if the receiver knows that you are receiving a signal of 1 volt, you can't give a gain of 1000 to the receiver, because if you give a gain of 1000, then it will saturate the receivers. It will amplify it so much that it will saturate it. You can't give that. Instead, you should have a gain of 1. When you receive, say, 1 millivolt peak to peak signal, then you need to have your gain of 1000. So you need to have some kind of a variable gain. So that's called as variable gain amplifier. So that's also a part of a receiver. Normally receivers also contain a block called as variable gain amplifier, which will vary the gain depending on the signal power that you receive. If you receive a very low signal power level, you will have a very huge gain. If you receive very high power signal power level, you will reduce your gain. Okay, so this operation performed by the receiver is called variable gain amplification. Now at the receiver, I don't have to give all the gain. For example, let's say you need a gain of 10 power 3000. I don't have to give all the gain in a single stage. In fact, I can spread the gain for multiple. This is the whole receive chain. I can have a gain of 10 at the LNA, maybe 10 at the band pass filter, and 10 at the even in fact mixers can also give you some gain. I can have the gain of 10 at low pass filter. So here I am spreading the gain. Okay, any circuit, any filter, when you have a gain, any kind of circuit is going to have some kind of nonlinearity. So this is why we want to analyze. If you see this, there is actually a cascade of nonlinear systems. Everywhere as the signal propagates through this chain, as the signal say propagates through this entire chain, the signal is going to undergo nonlinearity at every stage. So how do we analyze what happens to different parameters that we discussed so far? We discussed two important parameters to characterize nonlinearity. One is P1 dB, the 1 dB compression point. It tells you the point at which your gain is reducing. The second thing which was very important, which is IIP3, the third intercept point, input third intercept point. IP3 is the third intercept point, and when you refer it to the input, it's called third input intercept point. In IIP3, what we did was we fed a sinusoid, two closely spaced sinusoid of amplitude A, and then at see the frequencies, how did we choose them? We chose the frequency as f0 plus delta f, this as f0 plus 2 delta f. So, and then we said when you pass these through tones to a nonlinear system, they will introduce some small tone here on either sides. And these two terms, we call them as the intermodulation terms. Okay, these intermodulation terms are actually nothing but they are a result of third order nonlinearity. Okay, so what did we do is that in this third order nonlinear, what did we do is that we actually fed we just fed two signals of amplitude A, and then we measured the harmonic of the strength of the intermodulation component, which is IM component. And again, these two arises only because of third harmonic. If there was only second harmonic, you don't get these intermodulation terms. They arise only because of the presence of a third order nonlinearity. Okay, there is a third nonlinearity. When I said the nonlinearity model is modeled like this: k1x minus k3x cube. This x cube term was what that was giving rise to these two terms, the sideband terms, and that we called it as intermodulation products, IM products, and we said this level should be small enough. Always, we should be within acceptable limits. And AIIP3, we defined the term AIIP3 is that input. When I feed it, what happens is that as you keep increasing the input amplitude, this will increase linearly with the amplitude, but this guy will increase non-linearly. It will increase 3 times with the amplitude. Okay, and there will be one amplitude for the input sinusoid when the third harmonic power will become equal to the first harmonic. I mean the IM product, the intermodulation product term will become equal to the input signal itself, the amplitude of the input signal itself, and that point we called it as AIP3. In this lecture I will discuss about P1 dB, the effect of P1 dB in cascaded systems. The next lecture I will talk about AIP3, the effect of it in cascaded systems. So first we will talk about P1 dB, that is 1 dB compression point. Okay, so both are very important parameters. So we will talk about first 1 dB compression point. So now let's say I cascade two systems, nonlinear systems. Now the 1 dB compression point, I am going to call it A1, 1 dB for the first stage. The second stage is going to be A2, 1 dB. 1 dB compression point of the second stage. Both of them I am referring at the input. Okay. Now what we are going to do is that we are going to try to find what is the A1 dB of this whole composite system, or P1 dB was as well, they both are the same. What will be the A1 dB or P1 dB of the composite system? So how do you find 1 dB compression point? So you will feed an input sinusoid at frequency omega naught with an amplitude A, and then we will see the gain at this point, and we will find the input at which the overall gain reduces to 90% or reduces to 10% of its reduces by 10% of its nominal value. That I am going to call it A1 dB. This is the A1 dB of your overall amplifier. So I am going to assume the first stage amplifier f of x, I will call it f1 of x. The gain is alpha 1x. I will use alpha 1, that's what is used in your textbook as well. So I will use alpha 1. So this result is not derived in the textbook, but it's pretty simple. So I will derive it here. Alpha 1x minus alpha 3x cube. And for the second amplifier, I will assume the gain as beta 1x minus beta 3x cube. So now if you look at the overall gain is going to be alpha 1 and beta 1. That's the linear term gain. So that's your nominal gain for this system. Okay. So now what I will do is, if I am going to feed an input of A cos omega naught t as an input to the system. So first it will go through f1x. The output of that is going to be alpha 1a minus 3 by 4 alpha 3a cube into cos omega naught t, and then there is some term I'll call it this into cos 3 omega naught t. You will also have a 3 omega naught t at the output of the first amplifier. Now this signal is fed as an input to the second amplifier, which is f2 of x. Now here I will make some approximation. See, what am I interested when I am trying to compute the 1 dB compression point? I will just look at the first harmonic term. So we have to see what will lead to the first harmonic term. So I will take the first term. If I multiply it by, so the gain of the second is actually beta 1 x minus beta 3 x cube. So I will multiply by beta 1 the first term. So I will get alpha 1 beta 1 into A minus 3 by 4 alpha 3 beta 1 A cube. So that's the first term getting multiplied. Now if I pass this first term through the nonlinearity multiplied by beta 3, okay, then that term is going to produce a nonlinearity which will be given by minus 3 by 4 beta 3 into the amplitude of this whole cube into the first input amplitude, which is alpha 1 a minus 3 by 4 alpha 3 a cube, the whole cube. This will be the amplitude for the second stage. Okay, so the second stage amplitude is going to be Yeah, so this is the result for the second stage. Now here I'll make some approximations. So when I take beta 3 inside, I'm going to take beta 3 inside. What I'll get here is that, see, this term can be expressed as alpha 1 cube A. So it's a cubic expansion, I'll expand it. And then I'm going to multiply it by beta 3. I'll discard all the terms which have products of alpha 3 into beta 3, because alpha 3, it's a nonlinear system. Of course, we are going to have a small alpha 3. If you have large alpha 3, then there is no point of amplification to begin with. It's a nonlinear system, so we can't use it well. And if I take the product of alpha 3 into beta 3, that's going to be much smaller than alpha 1 into beta 3, okay, or yeah, mainly alpha 1, it's going to be much smaller. Any term which has a product of alpha 3 into beta 3 or alpha 3 into beta 3 square, alpha 3 into beta 3 cube, these are all going to be much smaller. These terms are all going to be very, very small compared to alpha 1 beta 3, because alpha 1 is going to be very large. Okay, it depends on the signal level, but the product terms, I can ignore most of the terms. So in this term, in this expression, I'll only consider one term, which is 3 by 4 beta 3 alpha 1 cube into a cube. This is the only term that will actually matter. Okay, there are a lot of other terms. I'm ignoring all the terms which contain products of alpha 3 into beta 3, because they are generally much smaller, because they both are product of two nonlinear terms, nonlinear coefficients, which will be smaller for a reasonably linear amplifier. Okay, so after that I can finally reduce my result to this. So finally I have these two terms, so which is alpha 1 beta 1 a minus 3 by 4 alpha 3 beta 1 a cube and beta 3 alpha 1 cube into a cube. So this is the overall expression we have for this amplifier. Now this expression has to be 0.89 into alpha 1 beta 1 into a, right? So alpha 1 beta 1 is a is the nominal gain, 0.89. If I'm trying to find the a 1 dB compression point, so if that value of a, for which it will become 0.89. So again I'll keep these two terms to this side and I'll bring this term to this side. I'll get 0.11 alpha 1 beta 1 a will be equal to 3 by 2 alpha 3 beta 1 a cube. Again I'll write it as plus 3 by 4 alpha 3 beta 1 plus beta 3 alpha 1 cube, the whole thing into a square. Now a cube, now I'll take a to this side, okay, and then I'll take 0.11 alpha 1 beta 1 to the denominator. So I'm going to get a and a square would cancel out, so you'll be left with 1 by a 1 dB square will be equal to 3 by 4 into alpha 3 by alpha 1 into 1 by 0.11 plus beta 3 alpha 1 cube. So alpha 1 would cancel out, so I'll get beta 3 by beta 1 into alpha 1 square into 1 by 0.11 into 3 by 4. Now remember, what is a 1 dB, the first stage 1 dB compression point, is simply given by root of 4 by 3 into 0.11. If you remember, I have written as 0.145, but that is nothing but 4 by 3 into 0.111 approximately into alpha 1 by alpha 3. Here it is modulus. I have not shown it explicitly here. So both, when I have written the model like this, alpha 1 minus alpha 3 x cube, it is assumed that the product of the coefficients here, I have written it as minus here. You can actually take a mod here, or both alpha 1 and alpha 3 will have same sign. That's all I'm saying. If I put a minus here, then they will have same sign. Okay, so this is just a small detail, you don't have to worry about it. So here in this expression, if you see, I've taken mod there, that is the value you get for a1 dB. And a2 1 dB, the 1 dB compression point of the second stage, will similarly be 4 by 3 into 0.11 into mod of beta 1 by beta 3. Okay, that's for the second stage. Now I'll look at this expression. If you look at this expression, it's nothing but 1 by a 1 dB square, a 1 dB compression point for the overall cascade is simply 1 by a first stage 1 dB compression point square, because there is no square root here, plus alpha 1 square by a 2 1 dB compression points a square. So this is a very interesting result. Okay. So what does this result tell you is that if you look at, say, let's try to look at the expression intuitively. So say this is a nonlinear characteristic of the first stage and then the nonlinear characteristic of the second stage. Okay. Now, if I have an amplification factor of alpha 1 in the first stage and alpha 2 in the second stage, okay, remember I am going to amplify a lot. If I have a large alpha 1, see, for example, I am sorry, this should be beta 1, this should be beta 1. So alpha 1 beta 1 is the overall gain. I am going to call it AV, but I am assuming your alpha 1 is much greater than beta 1. Most of the gain is in the first stage itself. If that happens, if you look at this term and the above mathematical expression, then it shows your A 1 dB square will simply be equal to alpha 1 square by A 2 1 dB. So you are limited by the second stage compression itself, and it should make sense because if your first stage gain is very high, intuitively you can see your A 1 dB will also be very high. You know, it depends, it's proportional to root of alpha 1. Also, you are going to amplify it so much that your amplitude is going to be very, very close to your amplitude. You are always going to operate in a very high amplitude level in the second stage. Okay, so all the nonlinearity that's going to come is going to come because your second stage is getting compressed, because your input signal level is so high that it's going to compress the second stage. Okay, so ideally if I want to have a very good nonlinearity, what I will do is that if I want to distribute again alpha 1 beta 1 as a total gain, I'll give all the gain for this, most of the gain for the second stage and very less gain for the first stage. Okay, so most of the compression will happen at the first stage itself because your alpha 1 is very small compared to beta 1. So in that case, my beta 1 will not undergo much of compression as much as the first stage will undergo. Okay, so both will determine equally. If, for example, I'll assume alpha 1 is 1. If alpha 1 is 1, then the first stage compression is determined, the first stage compression and the second stage compression will reduce the overall compression amplitude as well. What do I mean by that is that if you look at this expression here, what does this tell you is that the 1 dB compression point of the overall cascade of the two amplifiers will always be greater than, if you look at this expression, it will always be greater than the single stages. Any single stages 1 dB compression point. I'm sorry, it should be less. It should be less. I'm sorry. Okay, the 1 dB compression point should always be less than the compression point of the overall stage. Okay, I think I should not have made that statement. So if you actually look at it, let's say we had an ideal amplifier with a gain of alpha 1 for the first stage. There is no nonlinearity in it, and then I'm going to have a second stage with a nonlinear characteristic with some gain beta 1. Then if I apply a signal A here, the signal that's going to appear here is going to be alpha A1. Okay, so that's the signal that's going to appear at this point. Okay, and when you input refer it, to the overall input stage, yeah, it's going to reduce. Okay, fine. So I'll just express it from this point here. A 1 dB compression point should be equal to 1 by the first stage compression point square plus alpha 1 square by A 2. Okay, I'm sorry. So let's assume that alpha 1 is much greater than beta 1. Alpha 1 is much greater than beta 1 and both the stages have approximately same compression points. A 1 dB, one first stage compression point is very similar to second stage's compression point. Then we will try to see what happens in this result. So then your overall 1 dB compression point is going to be alpha 1 square by A2 1 dB square. So your A 1 dB of your overall amplifier is going to be A2 1 dB square, A2 1 dB by alpha 1. It gets divided, it becomes smaller. Okay, of course it has to be smaller. I'm sorry, I think I made that statement which was not correct. So if you cascade amplifiers, the overall amplification, the overall the nonlinear 1 dB compression point will obviously be smaller than the lowest one. Okay, this is a given result, you can take that. Okay, so it's going to be approximately A2 1 dB, which was approximately equal to A1 1 dB by alpha. So now if you see, it's significantly reduced. Okay, because the second stage also has the same 1 dB compression point. Okay, so which means you can't apply an input greater than A1 dB for the second stage, which means at the first stage, because the gain is alpha 1, you can't apply an input greater than A1 1 dB by alpha, because it's going to amplify by alpha in the first stage. That's the signal which the second stage is going to see. Okay, by alpha 1. So which is why you're going to, if let's say you give a signal greater than A1 dB for the first stage, then you are going to compress the second stage significantly. Okay, so final conclusion from this is that if you look at this expression, if I keep increasing alpha 1, then the A1 dB compression keeps reducing. So which means when I have a cascade of two amplifiers, it is better that I give most of the gain to the last stage. So that's the more important point that you guys need to understand. Okay, I'm sorry, I might have muddled up a little bit for a few seconds, so you can ignore that part. So if I have two amplifiers, alpha 1 and beta 1, you are cascading them, then it's preferred that you give most of the gain to the last stage. Okay, because if I have a higher gain for the first stage, then you saw that it's going to significantly compress the subsequent stages. So which is why when you want to distribute gain in a cascade of amplifiers, if your linearity is a big concern, then you should ensure that the final stage has the maximum gain and the first stage has the lowest gain. That's that's the way the gain should be distributed. But later we will see in noise, the gain distribution should be the opposite. So that's why you will have such contradicting requirements in RF. Okay, so keeping nonlinearity in mind, when you have a cascade of amplifiers, the last stage should have the highest gain, the first stage should have the minimum gain. Okay, that's what you get from this equation as well. Okay, so if I cascade say n number of stages, so I'll let the gain be alpha 1, beta 1, gamma 1, okay, and so on. So I have alpha, beta, gamma, then delta 1 and so on. Okay, then I can write the IIP3, the overall IIP3 as the overall A1 dB compression point as the first stage is 1 dB compression point. Okay, the second stages will get multiplied by alpha 1 square by A2 1 dB square, plus the third stage gets multiplied by alpha 1 beta 1 the whole square by A3 1 dB whole square and so on. So this is the fourth stage will be alpha 1 beta 1 gamma 1 the whole square by A4 1 dB square. So again we can see, if your alpha 1 beta 1 gamma 1, the overall gain is much greater than this and this and this, then only the last stage will dominate, and the A1 dB compression point of the last stage will simply be A4 1 dB by alpha 1 beta 1 gamma 1. So it just reduces significantly. Okay, so keeping this in mind, it's always preferred to give most of the gain to the last stage. So this is a general expression for 1 dB compression point in a cascaded system. In the next lecture, I'll talk about IIP3. It's a little bit more intuitive. It's a little bit more complicated to understand. So I'll talk about IIP3 in cascaded systems in the next lecture. I'll stop at this point.